Hi, welcome to the afternoon session. Let me to introduce Professor Babak Serradesh. Babak Serradesh is a theoretical physicist interested in quantum dynamics in condensed matter systems. He is especially interested in non-equilibrium dynamics and topology in many body systems and quantum field theories. He obtained his PhD at Simon Fraser University for work on high temperature superconductivity in cuprates. After postdoctoral fellowships at the University of British Columbia, he joined at Indiana University. He received the NSF Career Award in 2014 and was a guest scientist at the Max Planck Institute for the Physics of Complex Systems in Dresden. So it's a pleasure to introduce Professor Babak.
Thank you. Yep. All right, thank you. I think the sound is working. So, right, good. Thank you for this kind invitation and for your generous hospitality. It's my first time in UNAM, but also really the first time. I once passed through Mexico City, but first time Mexico City, so I'm really enjoying this trip. Thank you. So today I'm going to talk mostly about the title of the talk. But here is the plan. Let's see, the rough outline. So I'll do a little bit of introduction. There's already been some introduction, so I do a little bit of piggybacking on those introductions. My introduction will be mostly pictorial, so hopefully that will add a little bit of a different angle. And then I will talk today mostly about Floquet topological physics. And tomorrow, or not, second lecture, which is on Wednesday morning, I will give you some more examples of Floquet engineering, but also talk about a separate topic that is related to topology, but more inspired with, by my collaboration with our high energy physicists at IU, and especially at the IU Center for Space-Time Symmetries. All right, so let's see how much of this we can cover today, and we'll go forward. So not to forget, I just wanted to acknowledge many people who have worked on this topic in my own group and also collaborators listed here, and funding, of course, that has made this possible. So you already saw some of this introduction to equilibrium phases, which I'm representing here in this picture, various phases of water. And if you ask, I think, what is this picture showing? A lot of people will say that it shows a lot of symmetry, and that's not wrong. It's very beautiful and symmetric. That's sort of our concept of symmetry related to matter. But really, our understanding of how this is possible is not just based on the symmetry itself, but the broken symmetry. In this case, the translational symmetry in space that creates this lattice. This is, of course, applied to many other systems. That's a bismuth crystal, magnets, superconductors that break various different kinds of symmetry, and nicely summarized in Phil Anderson's aphorism, more is different. So I'm going to give you, as I said, a sort of a pictorial introduction. So this system is just let's say, an atomic limit of a chain, atoms sitting there with nucleus and say, one electron orbiting them. Of course, as you bring them closer to each other, these wave functions start to overlap, and you get, and that's kind of the sketch of the wave function, let's say amplitude. And you get something more similar to what is shown here, especially if I remove half of the electrons. Okay? So if I do that, then through that interaction, the electrons are going to be shared between two neighboring ions. And then the wave function will look something like this. But in choosing to show this picture, I've actually made a choice of doing this hybridization or superposition arbitrarily, from left to right. I could have also done equally a superposition that is shown in the other picture, in the faded picture. And because this is a quantum mechanical system, what happens is that you actually get a superposition of these two possibilities, and the actual wave function would look more something like this. Now, as I said, of course, there is rigorous mathematics behind this, but this shows you sort of why you have an extended state in this situation. So I'm going to sketch this with this diagram. So this is the wave function that is sort of shared across the system. And now we're going to look at what people have already shown in other talks. This is basically the quantum states labeled by the critical momentum, creating a band. Initially, I had all of the states filled, and that's represented by the chemical potential sitting at the top. By removing the electrons, I brought down this chemical potential to the middle, and I get this metallic state, which has basically vanishingly small energy cost for excitations. So this is a 1D system, and as Professor Fratkin showed in his talk, actually there's an instability here due to the interaction between the lattice motion and the electrons. And it turns out that that means that actually there's a little bit of distortion bringing the ions closer together, and that opens up a gap in this energy spectrum. So now there is a higher probability for the electrons to be near where the ions are closer to each other. So that is now shown in the sketch as a strengthening of the bond over here by a double line. The energy spectrum is gapped, and that's actually why it happens as an instability. It lowers the energy. Okay, this is of spontaneously broken lattice symmetries. We had a discrete translational symmetry already the free translation space lattice, but now the actual translation that the system is symmetric under is twice in space. Now again, I actually made a choice again, ions bring together, right, to create this structure. But really, there are two phases. So I could have also chosen to bring the other two ions closer to each other. So that creates another structure with the same energy in an infinite system, let's say. And now, the difference now is that this is actually a macroscopic structure. So what happens is that they have the same energy, but you don't normally form superpositions of these. Okay, so they sort of exist as classical background state for the electrons. All right. And this was discussed in. You can have these two structures coexisting along the chain, and that oh, sorry. I guess I don't have that slide yet. And something version. Right. Yeah. Yeah, I had to convert this from Apple Keynote to PowerPoint. A PDF had its own part. So you can imagine that. This is I don't know why it's showing here like this. I think it's actually showing right on my PowerPoint, but maybe on this computer it's not showing right. Okay, so we'll see how the rest of it shows. Right, there's actually a difference between these two structures that I represent this strengthening of the bond here by, let's say, in units of the background or background tunneling amplitude between the sites by some parameter. So M here is positive, this is stronger, and then this one is weaker. And that shows up in the structure. The two sites here and form a matrix Hamiltonian that acts on these two sites, basically. And this particular form of D is a complex number, and the difference between the two signs of M correspond to these two different structures that I was showing. Because for positive M, we'll have the strong bond here. For negative M, the other bond will be strong. And the difference is in the winding of this complex number d as a function of k. So this is a topological quantity. Okay, nothing is showing right. Maybe change to PDF, I think. Sorry, what did you say?
Maybe change the computer for, I think that PDF.
But I think they need this computer to be connected because of the system. Maybe I'll switch to the PDF. Okay. Can I use your connector again? Let's see if we can fix this.
You can use
I can use what?
the black.
I can write it, but that will take a lot of time, I think. Transfer the PDF. Thank you. Do you still have? Okay, sorry.
Ya lo pasó.
Ya lo pasó, sí. Okay. There we go. Ah, wait. Thank you. Yeah. Mhm. Okay. Okay, good. All right. So that's the winding number. Thank you. Sorry for this hiccup. Right, so it's basically the winding of this complex number. As I said, it basically looks at the phase. You know, here the phase is changing, but it goes positive, negative, and then comes back to 0. Here, it actually winds by 2 pi. So that difference of the winding number is a way to characterize the two structures. See this in a finite system through what is known as bulk boundary correspondence. If I look at a finite system, look at the different signs of the mass, you see the gap, of course, as I talked about before. And these states are the extended states, and right with the negative sign of the mass here, you get to 2 zero energy states. Those are bound to the edges. And all right. All of these, at the edge of the system, in the system, you could always have some bound state. The difference really is that in this case, the wave function might change, but energy is pinned to that particular value. So that's one way to tell sort of whether this is topological or not. This is very unlike any other sort of bound state. For impurities, where if you change the form of the potential of the impurity, of course, the energies will change. Okay, so I'm going to use this to introduce driven or out of equilibrium phases. Now, as Zaga shows, this is a little movie of how you can get an inverted pendulum to stabilize, right? And the way to do that, in this case, is to modulate the pivot point here at a certain frequency. I think in this case it was about 60 hertz. This is actually what Gerardo was talking about. The equation here is a kind of a Matthew equation, and it has regions of stability and instability in the other position, vertical position. Okay, so what we're going to use to describe this is, of course, full K theory. This was again mentioned in one of the other talks. So I'm just here just giving you a sort of a dictionary or a parallel translation. When you have time-independent Hamiltonian, you have sort of equilibrium dynamics, if you will. Of course, I have to be a little bit more careful here. Equilibrium, I should have said stationary dynamics here. Equilibrium really relates to having a bath. But the point is that this particular evolution operator is written simply as the exponential of the Hamiltonian times the time. You have stationary states. Those states are described by the time-independent Schrodinger equation as the eigenequation of the Hamiltonian, and energy is conserved. When you have time-dependent Hamiltonian, then this does not work, of course, because the Hamiltonian is time-dependent. But if you have a periodic dependence on time, you have some simplification that comes in terms of this Fouquet theorem. And it can be shown in this particular way that the time-ordered exponential that gives you the evolution operator is actually can be separated in two parts. So there is a phase part, and that is shown here. So again, there is a correspondence between this constant quantity and the energy. We call this the quasi-energy. And now there is the other part that used to be time independent, but now is time dependent, but it's periodic in time. Okay, so lots of times if you're familiar with, say, Bloch theorem for periodic, spatially periodic potentials, you might think of this as the Bloch theorem in time, with the difference that this was done before Bloch by Fouquet. So really, Bloch is Fouquet theorem in space, but that's how we learn it, I guess. And that equation that gives you phi is, whoops, I should go back, is written here. So you can think of this operator basically as an effective Hamiltonian with phi being the eigenstate and the quasi-energy epsilon being the eigenvalue. One thing that we should pay attention is, again, just like in the lattice case in space, this quasi-energy is a modular quantity because it's really only defined in terms of this exponential. And so we have to define zones for where it belongs. If I change from one zone to another, then I get a different coefficient up front, but I can combine that with the periodic piece. And that doesn't give me a new physical state. It's equivalent to the other one. So changing by multiples of the frequency omega does not really change the physical state. Sorry.
No, this is the answer to the question that Igor posed to me. If energy is conserved, that's quasi-energy.
Yes, right. So this is the coherent process, yeah. Okay, so let's go back to our system there. So this is really the Su-Schaefer-Heeger model, lattice model. And now what I'm going to do is that I'm going to make M time dependent. Okay, so this way I get a time dependent Hamiltonian. It's a sort of a toy model, if you will. And I'm going to make it time dependent in this particular way, which is very simple square wave dependence. The good thing about this is that I can actually calculate something analytically because it's just two pieces with constant m's. And here's the quasi-energy in some finite system with 200 sites. Note that the frequency is rather large in units of, the units are not given here. The unit is 1 for the hopping, right? And so the frequency is much larger than the width of this band, basically. Okay? So at this point, for this high frequency, the quasi-energy and energy are pretty much the same value. Modulating with such high frequency doesn't really change the eigenvalues doesn't make a big difference in the quasi-energies from the energies. The thing that it gives you is sort of an average between these two values, okay? Now I can change the frequency, so I'm going to change this vertical axis and turn it into a frequency axis. So the previous diagram is now just this two lines. And I'm going to change the frequency value. And this is what we will get. So again, we were down here. And note that I'm normalizing epsilon with omega, so I'm in this sort of Floquet zone, if you will. And then as I make omega smaller, I go this way. And eventually, this fan of quasi-energies reach the boundary of the Floquet zone. And something interesting happens there. We start to get these mid-gap states. And there's all sorts of other things happening as you make the frequency smaller and smaller. So as the frequency becomes comparable to the bandwidth, you start to get new interesting dynamics in the system. Note that the two values of m that I chose are both positive. So the average is also, of course, positive. And that's why on this side, in this finite system, I don't have any mid-gap states. This is basically topologically trivial, if you will. But as we go towards smaller frequency, now we have this bound states. So that's a signal maybe something interesting is happening topologically. I can look at those bound states. So in this case, I have these bound states here. Here I have over here at 0 quasi-energy. I have these two bound states. And you can even find regions where you can have more than one bound state, right, at different quasi-energies. Okay, so here really there are 4 bound states, 2 on this side and 2 on the other side. So note that the bound states, of course, these are orthogonal states. This is a Hermitian operator. The way that they're orthogonal here comes through the dependence on time. Okay. So I want to talk a little bit more about the structure of these. This is some work that we did some years ago, structure of these quasi-energy spectra. So looking at this, I'm going to label. This is actually something we did for fun, and we had a little bit of quarrel with the referee to use this musical notation. So this, this is the flat and the natural for the 0. Right, so those are the labels for those 0 quasi-energy, and then the other quasi-energy which sits at the edge of the zone. Now, I can count how many of these bound states I have, right? So we had 1, 2, and so on, and I can lower the quasi-energy, the frequency, and you can see this sort of evolution of the number of these bound states. They can start to change. So, how many you have in each gap is shown here. There's some kind of interesting increase in the number as I lower the frequency. So we wanted to understand what is this, what is happening here. All right, so I'm going to use a particular symmetry of the system to simplify the problem. And I saw this in our local restaurant, and I thought this was perfect. They're sitting next to each other, so I had to have a picture. So the system is quantum, and we're going to use the symmetry. The symmetry that has been discussed already is a chiral symmetry. So in the lattice, this is reflected as a sublattice symmetry of the two sides. So if I switch the sign, basically, of one of them, then the system is brought back to itself. I'm also going to add an additional symmetry in my protocol. So before I had this sort of two-value square wave time dependence, which has this symmetry that I'm talking about here, which is a mirror reflection in time. But any time dependence of this parameter, which has that, simplifies the problem greatly. How much time do I have? How much time do I have?
I don't know.
No, how much? 30 minutes? Or 30 minutes. Okay, good. More. Okay, great. All right. So this is work done by Asboth and company. And they showed that you can actually have something like the winding number that I was showing for the static system coming from the evolution operator. So what you're doing here is that you're calculating the evolution operator for in the middle of the cycle. And because the rest of the cycle is a mirror reflection of the first part, you can actually extract information for the whole evolution just from this operator. So I'm not going to go into the details of that, but we're going to use that result, which is I can take these coefficients of the matrix elements of the half-cycle evolution operator, B and D, so the off-diagonal and the diagonal, and calculate the winding number of those in K. So remember, this is now I'm using a periodic boundary condition. And those will give me exactly the number. So this is the bulk boundary correspondence in this case that will give me exact edge space. 0 or at. It also gives access as you look at
So on a previous slide, you had the W for the meaning on this?
Yes, so it's the same way of calculating the winding number, yes. So
But
you take this
yeah.
is a complex number, depends on the wind around the origin. Yeah.
Oh, I see.
Yeah,
Okay.
so that's the same
'Cause,
formula.
yeah. Based,
That was different.
okay,
Yeah, so
thanks.
here are two different. All right, so we can look at D, and D will have some shape in complex plane. It will look like this. So I'm going to label this a little bit so that I can count how many times it basically crosses the horizontal. Understand. The total number of crossings is the sum of these two, and the winding number is the difference. How many times you go, say, if I go this way, and then I go this way, right? That adds up. But so I have the crossings, and the winding comes from that. Well, the winding number is -1. And by the way, the sign is basically which direction you're going around the origin. All right. So there are processes as you change the frequency that these crossings change, right? So process, for example, of creating additional crossings. So this is going this way, you kind of get a kink, and then you go through. Now this does not change the winding number by itself because it basically adds a plus and a minus, right? And so that doesn't change the winding number, but it changes the total number of crossings. You can also sort of get rid of crossings. If I have a situation like I have here, I can form a kink and then sort of straighten it out. Again, that doesn't change the winding number. Okay. Again, unfortunately, it's not going to show. So it was that some winding here. As I lower, basically what is that it becomes more and more crossing. When I that to even look at it. Okay. Okay. Yes. Okay. So here's what we said. When we look at how many crossings you get here, we said, okay, let's just assume that we're going to get some kind of uniform distribution of these crossings because there's so many that maybe that's a good assumption. Okay, so that's an assumption. Now this means that n plus and n minus are going to have the same distribution. Now the thing that I can control is basically the length of this curve. And the length of the curve is related to the period of the drive. As I lower the frequency, the period increases, and the length of this curve becomes longer and longer. So we are expecting that the numbers of these crossings scale length. This kind of, with the period, sorry. This is kind of like a time of how much time you have to go up and down and circle around. All right, if this is true, if these assumptions are true, then the winding number, which is the difference between these two, is just a diffusive variable. It's basically, you can map it directly to a, you have some number of n plus, you have some number of n minus, and where you end up is exactly a random walk, right? So then you would expect, based on this assumption, that this winding number should show basically diffusive scaling behavior with time, with the period. Okay? And we can actually calculate what is the diffusion coefficient, because we could, in the case of a, this is a special case, in the case of a square wave drive, we have the two values, and we could calculate, the length, the complex function d or b, and then from the form of those, we could estimate what the diffusion constant should be. So this is an expression that comes analytically. And now we can compare to actual numerical exact calculations. Okay? So here, I'm showing you different protocols. So what are the values of M1 and M2? So you can start with positive. So this is a trivial phase in a static system. And M2 is the critical phase, right? You go between the two signs. And let's say this is the duration of the time of a period where you spend time in one or the other. Here we're taking them to be equal. And what I'm showing here is the gap in the spectrum and the winding number. Okay, so you see this sort of meandering winding number. The winding number only changes when the gaps close. So again, because of the analytical expression, we know exactly where the gap closes. So those are these dots. And exactly they map to where the winding number changes. Okay. Now, if I look at the several decades of frequency, so I start from sort of around 1, which is the width, the bandwidth of the system, and go, say, 1,000 times smaller, I can track these numbers. So how many M plus I have, the total, the winding number. I won't talk about this alpha. Alpha is basically, let me not talk about it. It was a check that we were doing on the data. And you can see that the number n plus really does go, this is a log-log plot, it does have this dependence on t. So that would be 1 over omega. So that's this line. And what you can't really see here is that this blue stuff, the winding number, this is the amplitude, the magnitude, so it doesn't show the sign, because we can't show the sign on the log scale. That's really the only reason. There is basically something like this. There's always a definite value of the winding number at any frequency, but it looks like a multi-valued function here. Like if I take a value here and go up, it looks like I have all these values. But they're really separated by very small differences in frequency. All right? If I look at a histogram, so for example, in this shaded area, if I look at all the values of the winding number and see how many times I get them, I get this Gaussian distribution. So this is sort of supporting evidence that the diffusion process that we were sort of at least postulating in terms of the distribution of n leading to the diffusion process is actually not far from the truth. So this would be a pseudo-random walk, right? Because again, so basically we have a random number generator in a sense. At any given frequency, you can calculate the winding number exactly, but as you change that frequency a little bit, sort of like seeding, the winding number fluctuates seemingly randomly. Okay, so we checked this in various different protocols. So I guess I will actually go over this and show you this. So in various different protocols, different values of these M's and so on, you can find the width of the distribution of the histogram that I was showing and compare that to the diffusion coefficient that we calculated analytically. And it matches rather well. So this is a line showing that these two are pretty comparable. Once you divide the width by this diffusion constant, you get an exact scaling with omega. Well, exact within our error bars for the size of the system and so on. Okay, so this is what we call universal fluctuations of these winding numbers. Now, there's precedence for this. This might appear sort of rather strange. We have a pseudo-random generator and so on. But actually, Chern numbers also show a similar behavior. So this is now in the winding number. Okay, I'm going to switch topics a little bit. If you have any questions about any of this, you can stop me, of course.
I have a question.
But yeah.
Because I was expecting that if your frequency goes to 0, you will recover like the adiabatic scene.
Right. The question is, if the frequency goes to 0, we should recover the adiabatic solution. And the adiabatic solution in that case, so you're going from M1 to M2, and if you can't, so two comments. So first, in the square wave, we don't have adiabatic. You have to jump from M1 to M2. So those jumps, sort of, in a sense, at the point of the jump, you're violating because you cannot do that smoothly, right? Right, you can make it smooth. Okay, so we actually looked at some smooth cases, and this persists. So the question then is, how do you get to a adiabatic limit, right? So what I didn't show you is the sign of the winding number, right? So you actually get positive and negative, right? So this is centered around 0, pretty much. If your system is really trivial, the mean value of the winding number is 0, and that's consistent with trivial adiabatic evolution in that situation. So again, remember that a small change in the frequency will have these, will have this winding number fluctuating. But if you can, so the way to see if you have this in that adiabatic limit is to be sensitive to the fluctuation. And you won't see that in just the winding number itself. You have to you have to be sensitive to its fluctuation or its variance. Yeah.
And also just a comment. We studied a similar system where if you take a graphene and a ribbon and you apply strain time dependence, you get exactly this model.
Okay, yeah, similar to the model. Yeah,
Exactly
okay, yeah. Yeah, I have a question.
Provided the evidence, the numerical evidence of this Gaussian distribution for the winding number, are you able to write down Langevin type stochastic equation for the winding number?
Yes, so I have to make some assumption about the distribution of these crossing points, because winding number is just a difference of them, right? So that was why we had this. So if you give me a distribution, then I can write it, right? So we assume that it's uniform. That was just an observation. Numerically, you look at it and it looks like it's everywhere. Then we can estimate that D. So the Langevin equation there is just a diffusion equation in that case. So we don't have that equation, but if I have a distribution, then I can, of course, find the distribution of nu. That's similar. So it's similar as writing a diffusion equation.
Yeah. Thank you.
Yep. All right, so I'm going to talk about a different kind of topology, which is this higher order topological phases. So this is, as I said, the Suchet-Verheugen model. Again, was mentioned also before in other talks. We have this sort of one-dimensional Dirac Hamiltonian from the linearization that Eduardo was talking about. This is the two-component spinner and so on. This is the bound state. And this is sort of that topological kink, right? So this can be generalized actually to higher dimensions as well in terms of the form of the Hamiltonian. And so here's an example going to 2 dimensions. There are some models that realize this. So for example, you can have a square lattice model with modulation again in 2 directions. So you have x and y direction. But in order to get the Dirac form, that's not enough. That's actually just a metallic state. What you need to do also is to get to basically decorate the lattice with pi fluxes. So every square has some magnetic field that gives you half of the quantum flux. And then you have topological, instead of kinks, you have topological vortices that basically combine shapes like this, for example. This is actually a Z4 kind of vortex where you get 4 domains with these modulations going in these directions and then put them together in this form. And indeed, this relates to another work by Jakiv and collaborators by Jakiv and Rossi. And the topological invariant here is the vorticity. So there are a number of zero modes corresponding exactly to the vorticity of this. So this is a single vortex. You can form other vortices that are double vortex or triple vortex and so on. And that gives rise to zero modes as well. So another way to realize this is actually in the honeycomb lattice, so related to graphene. There is a modulation of the lattice again, and this modulation decorates the lattice. And this modulation you can actually put on 3 different links, and those lead to 3 different domains. So if you want to form a vortex, now you have to bring these 3 different domains together. That's shown in this structure. And if you take, say, 2 of these, if there are both vortices, so this is the energy spectrum. This state here is actually doubly degenerate. There are 2 zero energy states, and I'm changing the distance between the 2 vortices. Right? As I bring them together, the number of zero modes remains the same. So you might say, okay, when they're far apart, you have 1 zero mode here and 1 zero mode here. When you bring them together, you get a double vortex, and you end up with 2 zero energy states. If you do that with a vortex and an anti-vortex, again, you have a zero mode here and a zero mode there. When you bring them up, close to each other, they start to split away. And at the end, you're left with no vortex, because vortex, anti-vortex cancel each other out. And these are things that were discussed in some papers that I was involved with. All right, maybe I will skip this in the interest of time. Now, the interesting thing here is, and this is something actually when I was doing the lattice simulations for this, or the diagonalizations for this, I would sometimes end up with vortices that were at the corner of the system. With zero energy states, bound states that were at the corner of the system. But I wasn't interested in the corners. So for me, that meant, oh, my vortex is malformed. It's kind of like is stuck at the corner of the system. And I could change the bonds and bring that vortex to the middle. And because you can't get rid of the vortex unless you do something, you can put it at the edge or in the bulk or something. But by doing smooth variations or flipping the values of m, you can't get rid of that vortex. That's why it's a topological structure. Then I could bring it in the middle and look at the structure and so on. What we didn't quite realize at the time was that this was actually a feature, it was not a bug. And this was realized later by Hughes, Bernavik, and Ben Alcázar, that related this to actually something in the bulk. So this is the topic of high order topological phases. Basically, what ends up happening is that this bound state in the bulk can be thought of as the corner state of one of these phases. Okay? So now we don't know which one in this picture. And sort of the contribution that Bernavik, Hughes, and Ben Alcázar made was to show what is the quantity that distinguishes the bulk of these domains, right? So which one actually is giving rise to this bound state. But this goes within a larger topic of higher order topological phases, where instead of having, so for example, in this situation, you have a topological insulator where the bulk is topological, separate from the say the vacuum outside, and the surfaces have gapless states. Here, the surface is also trivial, right? But the edges have gapless states, or even the corners, right? So this is 3D. The example that I was showing in the previous case is 2D. So, so basically, instead of having the edge of the system having edge modes, you have where the 2 edges come together, for example, forming a lower dimensional manifold, having a gapless mode. And this establishes a new kind of or higher order bulk boundary correspondence. Okay? So here's an example of how this could work. So this is a construction. So you can think of the surface of a topological insulator. This has basically a Dirac spectrum. And then you gap that out by adding basically a mass term to that Dirac Hamiltonian that represents magnetization. Okay? So if I have the sign of the magnetization change, then I'll have 2 domains with positive magnetization, negative magnetization. And you end up having a chiral edge mode right here, okay? So a Dirac Hamiltonian with a mass term here, which would go with sigma z, And if that sigma z changes sign, you get a bound state which can propagate along this edge. Okay? So now you can use this to form this system where you have a topological insulator, and you have gapped out the surfaces here by positive, negative values of m. And now you can see that this is the hinge of the three-dimensional system, having chiral nodes that go up, down, up, down. Right? Now, this is a construction. The thing that protects this, the symmetry that protects these hinge states, is the combination of, in this situation, it would be a reflection and a time reversal operation. Because when I do the reflection, this m goes to minus m, right? But if I do a time reversal operation, then again, m goes to minus m, because this is magnetization. And so that system goes back to itself, right? So the inversion and the time reversal symmetry combined is a symmetry of that system. Here it would be a rotation of 90-degree rotation and time reversal operation. Okay? So going back to this model, so now I call this the SSH cross tensor SSH model because it really comes in as that is the tensor structure of the Dirac Hamiltonian. Okay? Again, make m time dependent. Sort of do the similar thing that we did before with the one-dimensional system. Look at the energy, quasi-energy spectrum. And indeed, again, you can show that these corner modes form as I lower the frequency. But something else you can do here is to form vortices in a protocol that sort of you can think of as steering. And that's this protocol. So I have, let's say, a domain wall in my system. So with the hopping that I was showing before, maybe going this way, this one is shifted. And then in the other direction, and then shifted. So this is a domain wall. Now this is not a vortex. This is not a vortex. But if I go stroboscopically, periodically, between one and the other, even at high frequency, I will basically average these two structures. And if I average the two structures, then the average will give me the average of this and that gives me this arrow, this arrow, this arrow, this arrow. And that's a vortex. Right? So I can periodically go between two domain wall structures and form a vortex. And indeed, if you do that, you get quasi-energy like this, lower the frequency, and you get a bulk bound state. Okay, so that's the vortex bound state. But again, because this is so this is at high frequency, right? But as I lower the frequency, I get also bound states at the other edge of the quasi-energy zone. And so I end up having multiple bound states and so on that I can form in the periodic system. Okay, I don't know if I can see the slides. Okay, I will skip the slides. This is going a little bit into the way of characterizing the bulk boundary correspondence here. Which I think okay. Let's see. Yes. So I wanted to talk about graphene a little bit more. So this is actually kind of what started the full K topological phases, in a sense, in 2008, 2009. I just learned that a paper of Harari that I didn't know actually was right at the start, so my apologies if that is not cited here. But basically the idea here was that in a two-dimensional system you have you have the honeycomb lattice, you have Dirac spectrum already, as shown in other talks. And now you apply circularly polarized light, which breaks time reversal symmetry because of circular polarization. And as a result, you open up a gap that breaks time reversal symmetry. And so this should realize model equivalent topologically to the Haldane model that Eduardo, for example, was talking about. Again, this was a movie that you cannot show, the evolution of the quasi-energies that I cannot run here, basically showing various gap openings and closings. the thing that got started here in 2008-9 was realizing that that gap actually is there, and there is a non-zero Chern number that characterizes the bands. Okay, so this shows all of those closings in this diagram. We're tracking some of the high symmetry points. So there's gamma point, this is K point, M point, and so on. So what is not quite clear at this high frequency regime is that there is a gap, and you can kind of see it here now with the blue tracking the K point where the Dirac points are originally, and this gap scales quadratically with the frequency. Okay. You can also form, so this is in K space, and you can form Chern numbers, or really topological invariants, that characterize these energy bands. But now again, as before, we have two different winding invariants, one for each gap, right? So there's a gap in the middle of the quasi-energy spectrum, and there's another one at the edge zone, at the edge of the zone. So the regular Chern number is this red color, and you can see that it changes. I don't know if that color is clear. And there are two different ones. The C here, the regular Chern number of the band, is really the difference of these two. Okay? So I want to show you sort of quickly, even though there's sort of lots of formulas here, just to give you the sketch of how you calculate this, two invariants. So the idea is that if you had a periodic unitary operator, so whatever operator, as a function of, say, K and time, if it was coming back to itself, so this could be your evolution operator, because the evolution operator doesn't necessarily come back to itself, but if it was coming back to itself, then for a unitary that depends on these three parameters, the two Ks and a T, you can form a winding number that is shown here. And this is an integer number. Okay? Now, you're going to take the evolution operator and actually form a periodic unitary from it. And this is really what is known as the, in a sense, you can form it as what is known as the micromotion, right? The phase part of the Fouquet theorem. But the way you do it, for example, here, is that you actually enlarge, sorry, I shouldn't have this 1/2 here, so I should correct that. This is an enlarged period from 0 to 2t. Half of the period from 0 to t, you just evolve with the unitary operator, with the evolution operator. And then the other half, you come back with the phase, right? So this V here is just this phase factor for the Fouquet theorem. And so that winds you back to where you started. And so this particular unitary operator then goes back to itself. So there's some technical things about how to define the logarithm with the branch cut, and that actually tells you which gap you can access at the middle of the Fouquet zone or the edge. Okay? And then the winding numbers, or the Chern numbers that I was showing you, the topological invariants, are really these sort of winding numbers of this unitary that we form here. Okay, so if we do this, we can characterize the topological character of these bands. And you can also form an effective theory. So wherever the gap closing is happening, you can form, basically take the states that are closing the gap. There's two states, and you can create an effective theory of those two states, right? So this becomes a two-state sort of perturbation theory, if you will. Interestingly, at some of these high symmetry points, there's an additional symmetry that comes in, and I'm trying to show that here pictorially. So at the gamma point, that's the homogeneous sort of K dependence. As A goes around to a third of the period, it now looks right in the middle of the other two vectors that connect you to the nearest neighbors. And that looks exactly like what you started at. So there's an additional, actually at gamma point, there is actually a higher frequency here. It's 3 omega. Okay. And what that means is that to the lowest order, I can just look at the zeroth sort of Fourier transform, which is a Bessel function, and the higher order is going to be J3, and that's quite higher order. If I keep this argument small enough, and then I can ignore that. All right. Similarly, at the gamma point, you can calculate at the k point. Sorry, you can calculate the quasi-energies. And then there is a special interesting property, which is that at the gamma point, both states that are closing the gap have time dependence. Okay. At the k point, though, one of the components does not have time dependence. So this m, for example, you can set it to be 1 or 0, and then you can see that one of the components will not have time dependence. So one of the components is static. Let me skip this. Okay, so what does this mean? Let me skip this as well. What this means is that if I look at transport, as I'm shining this, driving the system coherently with the circular polarization, then transport actually comes from scattering states that come from the lead. So you can think of the lead, let's say, as other graphene parts of the system that are parts of the graphene that is not driven. And here the states are static, right? And so in order to make contact with the system, you have to have an overlap of the scattering states with the states within the system. Okay? And so usually this is some kind of resistance. This creates some kind of resistance depending on that overlap. But here we have an additional temporal dependence of the state here. So interestingly, that resistance depends also on the temporal character of the states. So if I have a clean system, so if we go and sit, say, at the critical point where one of these gap closings is happening, right? You can see here, for example, the gap closing at K, clean system. You have a gapless system, so you should have some conductance, and that actually is comparable to E squared over H because there's one channel here that is conducting within the bulk. Interestingly, if I look at the gamma point, remember that the gamma point was completely time dependent, right? It had no static part, and so the overlap with the static scattering states in the lead actually vanishes in the clean system. So as I make the system larger and larger, you can see that the conductance drops orders of magnitude. Okay? We can restore this overlap with the static systems if we spoil this symmetry that I was showing before by adding basically some disorder. So for example, you can add some disorder right around the leads and there restore some static component of the state. And that creates some positive, non-zero overlap with the static states in the lead, and that restores the conductance. So you can see this and this are 2 or 3 orders of magnitude larger. So this is sort of a disordered enhanced conductivity through the sample, which is, at least in order to understand it, you need to understand the temporal character of the states. I think I'm pretty much done here, so I will stop here. Is this a good time to stop?
Yeah.
Yeah, okay. And I will talk about this.
Okay, we thank again to Professor Babak. We have time for questions.
Perhaps you say it, but I'm missing. So what's the mechanism, like the physical mechanism to generate the vortex?
Good. Yes, so the question is, what is the physical mechanism to generate the vortex in the 2D system that I was showing? So there was no physical mechanism. We actually looked at some physical mechanisms. So you have to create these modulations, and then if that is done dynamically, then one of the excitations of the system could be a vortex state beyond, with some energy above that. But unlike the 1D system where the modulation happens as an instability through, with the interaction with the phonons, it's not an instability. You need a finite coupling with the phonons, for example, for this to happen. So we assumed the vortex and then studied its properties. Yes.
Yeah. So like what I'm perhaps missing is like what kind of system? Like what's the actual?
Okay. So you say some kind of square lattice system where the electrons are hopping. The lattice, of course, is a lattice of ions. So the electron-phonon interaction with the lattice can be, if it's large enough, can nucleate this transition to basically a bond charge density wave.
Okay.
Okay, but actually that's a good point probably to bring up, that you can also create the vortex dynamically. So if you could have this sort of, for example, in optical lattices, you can create the modulation through the optical lattice, and you can create a domain wall, let's say, in each direction, and by going back and forth between the two, you can create the vortex dynamically.
Any other question?
Well, thank you. Really nice talk. I'm wondering about this one. Is this
Yeah.
for tomorrow?
Yeah.
Yeah? Okay, so then
I'll talk about it,
can yeah.
Yeah, this is more recent work.
Yeah.
Sorry, I didn't get to it today. Yeah.
So, any last question? Yeah.
Can you use Floquet theory, or can you make any prediction for, well, instead of having a periodic system, a quasi-periodic system?
Yeah, we haven't really studied that, but there are other groups have. So you can, study basically the question. There are a number of questions you can ask. So for example, how robust is this sort of physics to aperiodic, noise or modulations, or whether that sort of aperiodic or quasi-periodic modulation itself can give you new phases. Yeah, other people have. Yeah.
Any other question? No, well,
I'm very curious about this vorticity. So like here in your system, like typically in quantum gas, like the quantization of the vortex or of the circulation around the vortex is a response of like superfluidity, but like here it's very different, right?
Right. You're asking if I guess I'm not understanding the question. So the vortex happens in the background, right?
Yeah.
So the vortex is sort of how the bonds are modulated. So that's kind of, you can think of it as a background field. It was the mass term in the Dirac Hamiltonian that is acting as sort of a classical field for the fermions. Are you asking if it can have its own dynamics, or?
I was wondering
Yeah, it can. So if it's generated dynamically, so through the interaction with phonons or some other mechanism relating to your first question, then it can have its own dynamics, right? So you sort of want to at least maybe, if you want to focus only on the fermionic response to it, you want to freeze out that dynamic. So you want to have energy scales that are maybe higher, or your temperature is lower compared to that, and so on.
Okay.
That's one thing I can say, but yeah.
well, we thank again to Professor Babak.
Thank you.
So we go to the last talk.
En el bolsillo, en el cinturón, donde se pueda. Donde se pueda. Sí, sí, sí. Sí, una abrocha. Bueno.
¿Puede ser ahí? ¿Puede ser ahí?
Ahí está.
Ok.
Es su agüita.
Ese es mi agua. Sí, sí, sí. Gracias. Ya
Yo
está.
le subo el volumen cuando vaya a empezar a hablar.
Perfecto.
Está normal,
Perfecto.
nadie lo va a escuchar.
Está bien, no,
Cuando empiece
hasta-
la plática, yo lo subo.
Ok, gracias. Ah, no me digas. ¿Qué hago? ¿Me traigo mi computadora? No se pudo. Ah, no se guardó. A ver, lo intentamos guardar. Sí, perdón. Acá en la mesa. Más fácil. Como que no se pasó. A ver. ¿Qué voy a hacer? Es descargar. A ver, pueden ver, sí, ya quedó. TQM, esa, a ver si ya quedó. No la quiere ver.
Es que es igual, son 500.
Sí, es que ese es el tamaño. Ese es el tamaño, 557 kilovatios. Y aquí sí la ve. Como gusten, sí podríamos hacerlo.
¿Se corta la transmisión en ese caso? No, no puede cortarse. Sí, no. Conectamos computadora, a ver si jala. Sí.
Aquí tengo adaptador. Acá está, sí, tiene suficiente. Sí. HDMI, ahí está. Sí, tiene batería suficiente. Sí. Ahí está. Tenemos que... Perdón. Dispositivo, pantalla.
Sí. Sí.
A ver, ahí se ve, no se ve.
¿Es un PDF?
Sí, es un PDF. Duplicar la pantalla. Perdón.
Hay que poner nada más
Duplicar la pantalla, ¿no?
duplicar pantalla.
Ahí se ve. Y ahí se ve. Ok. Y con eso.
Okay, we go with our last speaker. He's Professor Alfredo Raya from Universidad Michoacana de San Nicolás Hidalgo.
Okay, thank you all, first of all, to the organizers for inviting me to deliver this talk, then to all of you to keep on the expectation of the talk. It is very good to have such a nice workshop in this field that in Mexico is gaining even more adepts every time. So it's very good that we can discuss a little bit of what happens on quantum materials, quantum matter, and I will discuss something today that has to do with the Dirac equation with non-minimally coupled fields. And what I'm going to do in this regard, oh, oops, it's not working. So it is a work in progress with my collaborators, Juan Domingo and Eric, that are interested in this talk. And briefly, the table of contents of this has to do with something that I will present. What is the idea behind adding magnetic fields or electromagnetic fields to the dynamics of some physical systems? Then I will move slightly to something that we have already seen in this workshop, which has to do with the Yakif-Revy model, which has very interesting connection with a number of systems like the SSH system, topological systems, and many other systems that have these particular features. Let me see. No. So, Control L is not working. So let me just start briefly, but recalling what we all know, how to introduce the effect of external magnetic fields in the dynamics of charged particles. So, for instance, it is a very basic feature to understand cyclotron motion, and even in the classical level, and even going to the quantum spin dynamics. And it's the main part has to do with the modern cornerstone of physics, which has to do with gauge invariance. And through the introduction of electromagnetic interaction into the dynamics, we could take into account something that has to do with classical trajectories, quantum Hall effect, superconductivity, Landau levels, and many other of these concepts that we will hear repeatedly during this workshop that have to do with the dynamics of these charged particles. So whenever we are in the classical level, we have to start from the Lorentz force to see how these electric and magnetic field have influence on the dynamics of charged particles. And then we have to recall that these objects in here obey the Maxwell's equations that often allow us to introduce the auxiliary or electromagnetic fields like this. These magnetic fields in turn would not uniquely determine how we can fix this selection of potentials. So we have an additional freedom, which is called the gauge freedom in this case, and through this additional degree of freedom, we understand that even we can change these potentials to make the equations easier to solve in some situations. But the price to pay, or there is no price to pay, is because the magnetic field and the electric fields won't change. And that seemingly trivial observation is what allows the basics of modern physics through the fundamental interactions through the gauge principle. So what happens is that when we start with a free particle Lagrangian like this, we have to couple this free Lagrangian to electromagnetic potentials through a rule which is called the minimal substitution rule, such that the Lagrangian looks like this after we introduce the effect of the magnetic fields. So when we move from the classical realm and we go to quantum mechanics, of course we're going to start with a canonical quantization, and thus we, instead of working with the Lagrangian, we move to the Hamiltonian of the system, and the Hamiltonian of the system, when we introduce the electromagnetic potentials, we have to replace the kinetical momentum by the canonical momentum in this form, such that the Hamiltonian now acquires this form. When we quantize this system, then we move to operators, and then the Schrödinger Hamiltonian in turn has this form that appears in here. And with this Hamiltonian, what we actually have is that the gauge freedom allows us to transform simultaneously the gauge potentials or the electromagnetic potentials and the wave function, such that this Schrödinger equation doesn't change its form. And from this seemingly trivial principle again, we still have to, we still have that the physical observables do not depend on the choice of the gauge. In particular, when we solve the case of a uniform magnetic field pointing or aligning the C dimension, we naturally break the space dynamics into the parallel and transverse part of the dynamics. And in turn, when we use, for instance, what is called the Landau gauge, what we actually have is that the Schrödinger Hamiltonian allows us to map the problem of a particle in a magnetic field to a harmonic oscillator. And when we even move to the case of the Dirac equation, we still can have a dimensional reduction such that we can solve the same Landau problem in this case. The difference from the non-relativistic to the relativistic case is the behavior of the energy levels. Now, in the non-relativistic case, these are proportional to the cyclotron frequency that appears in here, but in the case of such that is linear in the principal quantum number, but when we move to the relativistic case, this behavior changes from the linear to a square root behavior on the principal quantum number. So what we have is the quantization of the orbits of charged particles in the xy plane, if my field points in the z direction. And here we also include, through the dynamics of the Dirac equation, spin and relativistic effects. So that means that we have the chance to include spin orbit and other effects into this framework in a natural way. So what happens when we want to do something similar in this sort of relativistic system in condensed matter domains? And I will start from the simplest configuration that I can think of, which is especially the dynamics, which I will call is relativistic in the sense that is dominated by a Dirac equation. And perhaps a simple model, the simplest model that I can think of is actually the Yakib-Revy model that has the dynamics of electrons in the continuum limit in one spatial dimension that appears in here. We have seen already a little bit on the discussion of this model, and this is because the model originally was developed in high energy physics, and is the model of a fermion field interacting with a spatially varying scalar field. And the thing of this model is that it exhibits zero modes, which are very interesting to explore, because these modes already include some very interesting feature that exhibits topological character of these objects. This topological system has solitons or domain walls in it, and we have seen that this is the solution when we basically are considering that the scalar field that comes in here can be written in terms of a mass term, which actually has a different sign in the left and in the right. These two guys don't need to be the same, these could be different constants. Nevertheless, there should be a difference of sign on one side and the other to exhibit this solitonic-like behavior that appears in here. So this model has a very interesting solutions. The zero modes that appear in here appears precisely as kinks that come in here, that they have this profile. And perhaps one of the first features that are very relevant is that it's the model that exhibits fractionalization of charges, even before people were discussing about the fractionalization of charges in the context of the quantum Hall effect, for instance. So, nevertheless, one of the aspects of this model that called the attention of our group is because they are tightly connected with topological insulator, because the gapless model that appear in this model appear at some interface that we can somehow model in here, and this appears at the interfaces where the bulk topological invariance change or flip sign in these domains. So perhaps when we have a succession of different materials, topological materials, we will find these models developing in the interface of the two. Now, from a solid state point of view, this Jakiv-Revy model can be seen as the continuum limit of other very interesting models itself, that is the SSH model, which was first introduced to describe the dynamics of polyacetylene chains that appear in here. And so in the tight binding approach, this model, this one-dimensional model, the SSH model, can be written in terms of these two hopping parameters that are alternating in a chain of atoms of different nature. And depending upon what are the edge states of this system, we could have topologically trivial or topologically non-trivial phases that appear in here. This model hosts topological edge states when the hopping amplitudes are reversed, and also the zero energy edge states are in correspondence in the continuum limit to the zero modes of the Jakiv-Revy model. Now, interestingly, this alternation of atoms of different spaces in a linear change can also be mimic in analogy with electric circuits, because if we have chains of capacitors and inductors in here, we could mimic the effect or the behavior of this change of atoms. And these type of systems are known in literature as topoelectric circuits, and this can be actually realized in a university lab. And because of this, one can study topological phases using classical electric components. We are just capacitors and inductors in here. And in here, we could find as well domain walls that correspond to the impedance mismatches of the edges of this change of electric circuits that we can construct. And the edge models are manifested because there are some modes localized or some resonances localized in the circuits on voltage and current distributions. So for instance, in this type of systems, what we can do is we have the pristine sample and we can start contaminating, that means adding impurities to the system simply by changing the values of the capacitors or the inductors that we are taking into account. That is something that with Eduardo and Julio have done in the past, and we have seen, for instance, how these resonances change as we move the position of the impurity in this kind of system. So these topoelectric circuits are systems that we can, in fact, they can allow us to go to the lab and see what are the predictions that we could have in the calculation in the computer and compare against what we can see in oscilloscopes and other electric apparatus that we could use. So the very interesting thing that we have in mind with this kind of systems is that the Jakiv-Revy model has also a compelling analogy with electrostatic systems. That means, imagine you have systems where you have two dielectric materials and a boundary between them, and then you can move or you can change the boundary and see that this electrostatic circuit or this electrostatic system can as well have, for instance, when we have a spatially varying mass term, can be matched or can be mapped to a charged surface or a potential interface that appear in here. And the zero modes would be seen as bound charges or field localized precisely at the boundaries. One of the other things that is compelling here is the fractionalization of charges can be seen as partial charges induced on conductors, and the topological nature here can be computed as surface integral of electric fluxes in this kind of system. So there are compelling features of this type of model that can be studied not only from a quantum point of view or quantum material point of view, but there are other physical systems in which we can make the analogy between them and see that we can even explore some topological features in the laboratory. So, what I want to show you has to do with some ideas that we were discussing with Juan Domingo and Eric that has to do with something that actually was developed here, is the Dirac-Moshinsky-Szczepaniak oscillator, and this has to do on how to introduce the influence of the fields through a non-minimal coupling. That is, I will change the rule of simply replacing the momentum by the momentum and the the magnetic potential in terms of some new rule that is non-minimal in the following sense. When we talk about the Dirac oscillator, we basically imagine a particle, an electron, for instance, trapped or bound in the potential of a harmonic oscillator in this case. If I go to solve this problem from the quantum mechanical point of view, it's a straightforward, and the energy levels, let me call it just energy levels, appear in this form in the case of a simple Dirac oscillator. But then the idea of Moshinsky and Szczepaniak here was to replace the momentum by this operator that appears in here, such that the momentum is changed linearly with the position in terms of a gamma phi matrix. So this non-minimal rule has a number of features that are very interesting to explore, but in particular, the Hamiltonian looks like this, and it changes, it moves the energy levels by this form, in what this constant has to do with how to introduce this particular form that appears in here. That is, the energy levels are shifted slightly from the ordinary levels in terms of how we introduce such a non-minimal coupling rule. So this Dirac-Moshinsky-Szczepaniak oscillator already introduces some spin-orbit coupling that is interesting to address within the context of topological insulators. Also, the energy modifications allow us to have a completely different dynamics in the system, and there is, when we want to understand the dynamics of position and spin in more complicated system, perhaps the minimal rule substitution is not enough, and maybe this could be a first step towards this kind of description. Now, as you have imagined already, it has some symmetry breaking features, with, in particular, for Lorentz symmetry breaking, could be very interesting to explore or to address in different systems. And in other lower dimensional systems, such as graphene, can be mapped to position-dependent masses. So in that regard, this Dirac-Moshinsky-Szczepaniak oscillator already introduces some very interesting features that can be described within the topological matter context, and that are good to address. And so what I want to show you next is some work in progress that is basically thinking aloud, thinking and sharing with friends some ideas that could be interesting to explore, because we have Eric on one side and Juan Domingo on the other side, which have the techniques and the time to do these calculations. And basically, what one can do is try to see this Dirac-Moshinsky-Szczepaniak oscillator in the following context. What happens if I move the dynamics, instead of a four-dimensional space-time of particle physics, to a one-dimensional, 1 + 1 dimensional space, and I consider a shifting of the momentum in a non-minimal fashion that appears in here in terms of a Dirac Hamiltonian, which has this form. So when I write down the spinor in this case, I will easily end up with a couple of independent Schrödinger-like equations where there is an appearance of a potential in here that has to do with what do I write in here, and it's a very suggestive notation because I will relate it somehow to some electric field and some potential of reference, but this form that appears in here has precisely the shape of a supersymmetric quantum mechanical problem. And so from this point of view, I can solve for the zero modes, and I can observe that the two components of these problems are these two combinations that come in here. Now, the interesting point to note is that these two zero modes are not normalizable simultaneously. I have to choose one or the other. And this is because the two pairs of Hamiltonians that appear here already, on top of all the symmetries that I have already discussed, they exhibit the supersymmetry that comes in here. And so basically, what I can think of is imagine two dielectric materials separated by an infinite charge sheet of this form with a uniform surface charge that comes in here. So this is a problem that we have all solved in the undergrad studies, and we have the electric field that is a constant, but a different constant on the left and on the right. And this constant field emerges from a potential that varies linearly, but again with a sign difference in both sides. In terms of some dielectric constant that characterize these materials. So these two materials actually don't have to be the same. They could be completely different on one side and the other, and what I will end up with the solution of the Dirac equation here is precisely a solitonic solution which has this profile in terms of this potential, electric potential that comes in here. This was discussed some time ago by Gonzalez and the group, and what we can do in this regard is, and this is, again, just work in progress. We have already considered what happens if instead of a linearly changing potential or a linearly changing substitution in here, in the non-minimal coupling, we add some more general Hamiltonian that has this profile. And when we consider this Hamiltonian, we again can lead the equations of motion to a pair of Schrödinger-like Hamiltonians that have this generic form depending upon the shape of this object here that within the context of supersymmetric quantum mechanics would be referred to as the superpotential. And of course, we can obtain the zero modes again in terms of the integration of this superpotential that comes in here. Again, the observation is that these two guys are not simultaneously normalizable, so I have to pick one or the other. And what we are planning to do, and this is precisely what Eric will do in the next few weeks, is try to make a catalog of what are the zero modes that can be solved analytically, and what is the behavior of this King's solution for different shapes of the potential. And so what can we interpret from this spin-orbit coupling in such systems that are coming here that are relevant from the numerical point of view as well to the field of topological insulators. Moreover, we want to establish connections with topological phases, either in the SSH model, but also with topoelectric circuits, and all this job that comes in here that can be done in principle, and that until we start writing down the equations and seeing what is that we have to explore, we will be able to report somewhere. But this is, again, some of the ideas that we have in mind and that we consider that could be relevant for this community and in different avenues that we can explore, either directly from the calculational point of view, but relating it to topological materials and also to some classical systems that can be mapped or can be explored in the laboratory. And with this, I thank you for your attention. Thank you.
Questions?
You mentioned the three-dimensional harmonic oscillator of Moshinsky and Stepaniak, but I didn't see the results. You put only the one-dimensional example? Or?
No. In this case, the solutions of these are this is the Dirac-Moshinsky Hamiltonian and Stepaniak Hamiltonian, and the only thing that I wrote down was the energy levels in here that are shifted from the ordinary case, but in terms of this constant that is relevant to how do we introduce the non. It comes in here. I mean, when we have Again, when we have the full Hamiltonian in 4 dimensions, we still have the angular momentum and the spin separation, and we could have a term that modifies the spin-orbit coupling. In just coordinates, to make the transformation of coordinates to make it explicit. Yeah, the eigenvalues do not show this part. You're right. I haven't written explicitly here the angular momentum appearing in those states. You're correct.
I'm sorry, I got lost. Which is your Hamiltonian, which with the Dirac oscillator, which is supersymmetric?
Let me just go here. Here. This is my model of the Dirac Hamiltonian with non-minimal coupling of some external field, and these are, when I write down the equations for each of the components,
yes,
I end up with 2 Schrödinger supersymmetric pairs.
Yeah, but this is the normals. Where is the Dirac, I mean the Mochinsky contribution, gamma 5?
Well, in 1 dimension, you have this that makes the role of the chirality operator, yes.
Okay, thank you.
Any other question?
I really like the presentation. I have just one question or maybe clarification. So when you have the Dirac equation with that harmonic oscillator, so I guess what I want to say is this is the first time I see it the way you wrote it, because I mean one part is linear, but then you have the the x square on this, and it seems that it's kind of getting rid of the zero. N0 solution. I kind of wonder if you could comment on that, right? Because your solution, when you do the kind of the usual, Landau level there, then the 1/2 goes away, and you have, the 0 level gets polarized. Yeah.
We have to work the details in this particular case, but what you are actually seeing is precisely that here, in spite of the fact that you have a linear contribution that goes with the position, you also have a quadratic contribution that comes in here. So this replacement, as we mentioned earlier, is we need to take into account also the angular momentum, but yes, you have to see what are the states that are missing under this replacement, this non-minimal coupling. Yeah. Mm-hmm.
Any other question? So I have the same question. This is a variation of the Mochinsky oscillator, right?
Yes,
because of the Mochinsky oscillator is only with the minimal coupling.
That is correct. Yeah.
Non-minimal coupling.
Yeah. Only without this term. Yes.
Yeah. But also in the original paper by Mochinsky is with a beta matrix, not with gamma 5.
That is correct. It's a Not with gamma 5, is this with the 2 sigmas that are coming here.
Yeah,
Sigma X, sigma
sometimes
Z.
gamma 5 is associated with pseudo fields, right?
That is correct,
Yeah.
yes.
If we do not have any other question, so we thank you to Alfredo. Okay.
Muchas gracias.
So we have the poster session outside along this wall, and we have coffee and cookies also.
Muy bien.
See you tomorrow.
Alfredo Reyes, servidor.
La pregunta es en la